Both lectures 19a and 19b of differential equations and linear algebra are pretty heavy duty on some theory. As always, as you try to understand the theory, you want to think about examples, but you also need to have modes of thought that help you think through the theory even without the examples. You need to use your imagination, actually. Imagination is an important part of being successful in math. In lecture 19a, we're going to start by looking at an applied problem, something called the Unforced Van Der Pol equation, which is related to special kinds of electric circuits, and the corresponding system. We'll look at its phase plane and the flow, which again means a family of flow maps. Then we'll try to approximate the solutions with Euler's method in n dimensions, though n in this case will be 2. Lecture 19b continues to be pretty heavy duty on the theoretical linear algebra. All right, so what is this unforced Van Der Pol equation and the corresponding system? I'm just going to show you the equation initially as a second order equation. I'll talk a little bit about the electronic application, but I really don't know much about the electronic application to tell you the truth, but we can still think about it intuitively. We'll look at the corresponding system, and again, we're trying to get to the phase plane. So here it is. It's a second order nonlinear, emphasis on that word nonlinear, family of ODEs with a parameter in it, epsilon. The epsilon that you see here, that is a parameter. And that's why this is a family of equations. Second order involves a second derivative as the highest derivative. It's also got a first derivative. It also has the function x itself. X is a function of t here. Where's the nonlinearity? It's in the x squared right there. There's the nonlinear part. And that means that you can't solve it. You can't find solutions of initial value problems, at least not with functions that you're used to. I do want to use Mathematica in both lectures today, and in fact I want to use it as we go instead of waiting for the end. So let's look at Mathematica. Can ND solve value solve the Van Der Pol equation? It's thinking, 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 and I waited a while and it didn't spit out an answer for this one. So I decided to abort the evaluation, and I will do that now. I wondered maybe if I added initial conditions in here, x of 0 equals 1, say, and x prime of 0 equals 0, two initial conditions for a second order equation, maybe that could do it. And it's still thinking, 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 it's not sure what to do. Let's go ahead and stop that evaluation. Then I thought, well, maybe if I pick something special for epsilon, like epsilon equals 1, maybe it'll work then. And here, well, it's doing something different than what I did on my computer. On my computer, it just spit back what I typed. There it goes. It just essentially gave up. It doesn't know what to do. Why? Because the equation is too difficult. Okay, nobody has defined a name for the solution of this function, evidently. You could give it a name. You could name it after yourself, perhaps. Well, at least if you found a good application for it. So we need to think about it qualitatively and numerically. That's the point. Let's go back to the PowerPoint. What is the corresponding system? That's what we're after next. That will allow us to ultimately think about the flow, like we've been talking about in recent lectures. Here's just a comment. This differential equation is used to model an electric circuit with a triode valve whose resistive properties change with the current, including having, this sounds strange, a negative resistance when the current is low. This is essentially like a negative damping. It's okay if you don't quite understand this. I don't really fully understand this. It's okay. I mean, if you want to be an electrical engineer, you should ultimately try to understand something like this. I don't know what kind of circuit would do this. The negative damping evidently means when the oscillations in the current, or perhaps in the voltage, are small, that it actually amplifies instead of damping. To call it a negative damping means it probably amplifies the signal. That's probably what happens, and in fact, that's what we're going to see happens. How do you convert it to a system? Let y equal dx dt. That's a scalar quantity. Let boldface y be the vector xy. I've shown you this before with this t here. That's not a power. That stands for transpose. I've mentioned that before in the linear algebra portions. It's just shorthand notation, in this case, for the column vector xy that I didn't really have room to put in here. by putting the transpose there, that whole thing represents the column vector. And we've been typically writing our vectors as column vectors. What's the corresponding nonlinear autonomous system? It's this. Let's think it through. So boldface y, boldface vector y has components. First component, little x. Second component, little y. These things are functions of t. Its derivative with respect to t is found by differentiating each component. Ignore this for the moment. Jump over to here. dx dt equals y. Where does that come from? That just comes from right there. The definition of what y is. And then dy dt equals this thing. Where does that come from? That comes from the second order equation. Because the second derivative of x with respect to time twice is the same as the first derivative of y with respect to time twice. And if you subtract x from both sides to get a minus x on the right, and also subtract this term from both sides to get a minus epsilon x squared minus 1 times this thing is y. Okay, so that's what the vector field is essentially. And that's what this notation means right here. Boldface f of y represents the vector field. The input is y. You think of the inputs of vector fields as being points. The output is f of y. You think of the outputs as being arrows, vectors. Why is there an epsilon there? Well, because their parameter epsilon is in the formula. Think of epsilon as a constant. There's a key step. Think of epsilon as a constant. That's a conceptual thing to do. You could write this in different ways. You could multiply the minus epsilon y through this parentheses there, and you get this. Double check that. And if you wanted to, you could also sort of separate the linear part. I might call that the linear part of the vector field. And you could write that in terms of a matrix multiplication if you wanted to. And over here, you've got the nonlinear part. That might be helpful sometimes to separate those two things. What do we want to do? We want to draw the phase plane. We could ask, what are the nullclines? What are the equilibrium points? What do the direction field and the solution curve look like in the phase plane? Let's do that by hand. And then I'll show you what Mathematica produces. Let's take epsilon to be 1 to keep things simple. What about the x nullcline? That's the best thing to do first, is think about the nullclines. That's where dx dt is 0, and solutions cross the x nullcline with vertical tangents. The first component of their velocity vectors is 0. Or if the x nullcline happens to be a vertical line, then they stay on that vertical line. dx dt is y. That's going to be 0 and y is 0. Which is the x-axis. That's where y is 0. You're going to cross the x-axis with vertical tangents. What about the y nullcline? That's a bit more complicated here. That's where dy dt is 0, where this is 0. If I set that equal to 0, can I solve for y as a function of x? Yeah, I can. I could, if I imagine setting this equal to 0, I could add x to both sides, and then I could divide both sides by negative epsilon over x squared minus 1. Y would be x over negative epsilon over x squared minus 1. You can get rid of that negative sign if you like by switching around the x squared minus 1 to be a 1 minus x squared. And if epsilon equals 1, then it becomes this, when epsilon is 1. Okay, a rational function of x. What would its graph look like? I guess it would have a couple of vertical asymptotes at x equals plus or minus 1. And an x-intercept is 0, and that would also be the y-intercept. And you could go ahead and use your technology, your graphing calculator, say, to graph that, or Desmos or whatever you want. The y nullcline is going to have vertical asymptotes at 1 and negative 1. And you can also graph it outside of that range. When x is bigger than 1, you'll find the graph looks like this. When x is less than negative 1, you'll find the graph looks like that. That's the y nullcline. Solutions cross that with horizontal tangents. It's got 3 pieces to it. And again, the x nullcline is where y is 0, the x-axis. That's where you cross with vertical tangents. Where x and y nullclines intersect, which is only at one point, the origin right there, there you have an equilibrium point. They don't cross over here because the y nullcline is asymptotic to the x-axis without actually touching it. It's almost like it's close to being an equilibrium point, or it gets closer and closer, but it never actually is one when you go past there. How do you draw the rest of the phase plane? You use the nullclines, and you also need to think about the sign of the derivative for each situation for x and y individually, positive or negative in the different regions. Since dx dt is y, dx dt is going to be positive, velocity vectors of solution curves will be pointing to the right when y is positive. So when you're above the x-axis, solution curves move to the right, not necessarily horizontally, of course. And when you're below the x-axis, solution curves move to the left. Y is negative. dy dt is more complicated. It equals this. Where is that positive and where is it negative? It's trickier. I usually like picking test points. Like I could pick a test point on the y-axis where x is 0 and y is positive. And imagine plugging it into the right-hand side of the dy dt equation. When x is 0 and y is positive, think about it here. That's 0, this is positive. Epsilon is greater than or equal to 0. And really, I'm assuming epsilon is, well, positive. It's 1 in this case. Dy dt would be positive. So in this region in here, above this part of the y nullcline and below that part, solutions are going to move upward. And you can check that in here, they'll move downward. Over here, they'll move upward. And over there, they'll move downward. You can double check that. Putting all this information together, you can try to draw some solution curves. I'm just going to make a real quick sketch of some. Remember, got to cross those nullclines in this kind of way. These things are hard to get perfect. Nobody can draw them perfectly. But I'm seeing one solution curve that's maybe looking about like this, with an initial condition over there. And maybe another one if I start close to the origin and kind of follow the way I'd have to go, might look about like this. People typically have a hard time with this, but practice helps you get better. And I could draw on more. Interesting. The initial condition over here led to kind of oscillatory behavior in about this range right in here. And the initial condition right there seems to lead to oscillatory behavior in about the same kind of range of values, about some sort of oval about like this. Interesting. I wonder if there's a solution that always comes back to where it starts. A periodic solution. There is. We'll look at Mathematica here. Let's go ahead and do that now. This is code that enters the vector field here. This is code that solves for the y nullcline and the equilibrium points, which is just one of them at the origin. This code will give me the phase plane for any value of epsilon that I might want to plug in, like 1. Here it is. Hey, and that looks pretty similar to what I had. This code animates it as epsilon changes. I can make epsilon bigger. It's still a similar kind of phase plane, similar kinds of nullclines and similar kind of behavior, just a little bit more extreme, you might say. And I can make epsilon smaller. Okay, so this code, I'll put in the Google Drive and you can download and play with if you want, can make the phase plane. Let's go back to the PowerPoint. And here it is. Here's a screenshot of the phase plane. What do we see? We see the x nullcline, that's the x-axis, in green. Solution curves cross that vertically, going downward over here and upward over there. We see the y nullcline in brown. 3 pieces, here, here, and here. Solutions cross that horizontally. Leftward pointing out down here, rightward pointing over here. You got one equilibrium point at the origin where brown and green intersect. And yeah, the computer's doing a better job drawing what's going on here. Where is the possible periodic solution? Again, it's hard to draw these things perfectly, but as I look at this, I'm thinking maybe somewhere right in this ballpark. Yeah, it's not perfect, but I'm not too far. Maybe a little closer would be the true periodic solution. There is a periodic solution. Proving that a periodic solution exists, it's called a limit cycle, also called an attractor because it's attracting nearby solutions. It's like some sort of sink, except it's not a sink in the usual sense. It's not an equilibrium point. Proving that exists is actually kind of hard, but also kind of interesting. You can create something called a trapping region. And using something called the Poincaré-Bendixson Theorem, which we will talk about later in the semester here, later in the course, you can prove that this periodic solution exists. Basically, a trapping region is a region, it's very difficult to draw, somewhere around this periodic solution that you want to prove exists, along whose boundary you can prove that the vector field always points inward into the set. That is the trapping region. I'm trying to shade the trapping region here. It's kind of a ring shape. I'm trying to shade here. If you can construct such a ring shape where the vector field is pointing inward along the boundary, and I'm not saying that's an easy thing to do, you can use something called the Poincaré-Bendixson Theorem, and the fact that the only equilibrium point is not inside the shaded region to prove there must be a periodic solution. Okay, but that's kind of a high-level theorem, the Poincaré-Bendixson theorem. But I hope you think that's kind of interesting. We're about to talk about the flow some more. What is the flow? Remember, the flow is, well, first of all, it's a family of flow maps, time t flow maps, like time 1 flow map being the most common thing to think about. And what we're really interested in, keep this in mind, this is very important to be thinking about as I talk. We're interested in realizing that for an autonomous equation, you can follow solution curves by iterating the flow map. There's a difference equation involving the flow map whose solution is very much tied to the solution of the differential equation. Relationships between difference equations and differential equations is what we're after. Easiest in the linear case, and there the matrix exponential is helpful. Harder in nonlinear cases. We're interested in the picture. We're also interested in the behavior of solutions. We're also interested in images of the flow map. Images of sets under the flow map. Like I could have a set, let's say, that looks like this. A set of initial conditions. And I might ask, as time goes by, say 1 unit of time goes by, where do all these points get mapped to under the flow? In other words, what are all the endpoints of the solution curves for these various initial conditions after, say, 1 unit of time? Maybe it's over here. If that's the case, then the flow map, the time 1 flow map, say, would map this set to this set. I could call it phi1, phi superscript 1. It would map this set to this set. When the system is linear, this will be a linear transformation. When the system is nonlinear, as this is, it's not a linear transformation, it's a nonlinear transformation, which of course then makes it more difficult. But the idea still holds. Flow maps are also helpful for other things, visualizing things as we will see even in this lecture, and creating some definitions later in the course that will be helpful for us. So what is the flow of the Unforced Van Der Pol system? Okay. Well, first of all, the right-hand side function is nice. VDP stands for Van Der Pol. It's a vector field. I didn't put a subscript of an epsilon here, but pretend there is one. We'll go ahead and write it by hand there. It's nice. It had a nice formula involving x and y and epsilon. And there was only a small nonlinear part, forgot what it involved. It involved x squared, I think. I should go back there. Whoops. Oops, there it is. Negative x squared y, that's the nonlinear part. It's nonlinear, but it's a relatively nice formula. It's nice and continuous. The components are nice differentiable functions. You could even say continuously differentiable. The derivatives exist in our continuous functions. In fact, you could say it's infinitely continuously differentiable. Though if you keep differentiating, since it's a polynomial terms, you're eventually going to get 0. That doesn't happen with things like cosines and sines. Solutions to these initial value problems will certainly exist and be unique over some time interval centered at time 0. Why? Well, it's a theorem that we're going to focus on some in lecture 20a, an existence and uniqueness theorem for these higher dimensional problems. We talked about existence and uniqueness back in chapter 1 for scalar differential equations. Now we're going to generalize to higher dimensions again in lecture 20a. That's the next one. They exist and are unique because it's a nice function, essentially. The time interval could be a tiny time interval. It could be, in general. However, because the Van Der Pol system has a global attractor, that periodic solution attracts all solutions except for the origin. Because of that, solutions don't go off to infinity as t increases. And so you can actually prove with the Van Der Pol equation, though it's a difficult proof, that solutions exist for all t greater than or equal to 0. For any fixed epsilon, think of that as fixed when you're thinking about this content here. Though I could change what it is. I could think about it for epsilon as 1, I could think about it for epsilon as 2, I could think about it for epsilon as 0.1. No matter what fixed epsilon I picked, it can be shown that solutions of all IVPs exist and are unique for all t greater than or equal to 0 out forever. T can be as large as you want. Okay? Not proving that, that's a difficult proof. Okay, but I hope it's believable. And it's because that periodic solution is attracting other solutions. So they can't possibly go off to infinity. And maybe in an infinite time, like a vertical asymptote type of thing. All right, here things are getting more abstract. It's going to be helpful when you see the symbols I'm about to show you to pretend the symbols are simple formulas, even though in reality there are no simple formulas for them. But just pretend. If we write the unique solution for generic IVP using this notation, capital Phi, why capital instead of lowercase? Because this is a higher dimensional problem. It's kind of like a vector. I mean, I could have bold-faced it as well, but capital Phi sub boldface y0, ignore the epsilon for the moment, of t. That would be a symbol for the unique solution of the initial value problem to this, right here, and will be defined for all t greater than or equal to 0 based on what I just said. And the epsilon is just emphasizing the system does depend on epsilon. So when you look at this, just pretend epsilon is some fixed number that's greater than or equal to 0. And pretend this has some formula. Maybe simple, maybe extremely complicated. It doesn't have a formula, but pretend. It's helpful to pretend. We can then say that it follows that, since it solved the differential equation, when I take its derivative with respect to t, thinking of y0 and epsilon is fixed, that's the left-hand side of the differential equation. I'm plugging the function into the left-hand side. That I will get when I plug it into the right-hand side in place of y. This part matches this part. You know what? All along I have been emphasizing to check functions or solutions of differential equations, you plug into the left-hand side or the right-hand side, do they simplify to the same thing or not? I don't have formulas here, so I have to pretend. And I can say, since it is a solution, this will be true, but it's true in a more abstract sense. It can be proved to be true. And that's what a solution means. So proving it's true means you need to show the solution does exist. And with the initial condition, it is unique. It satisfies that initial condition. Now, I'm not saying those are easy proofs. Those are pretty high-level proofs involving some real advanced real analysis. But at the moment, we just need to pretend. And it's worthwhile pretending because it helps you understand the meaning of things. So it's still worthwhile to do. We can also define, as we talked about the last couple lectures, 17a and 17b, for any non-negative t, the corresponding time t flow map with the different notation of fancy phi, cursive phi. The epsilon is just a subscript here that just pretend it's constant. The t is a superscript, like we've done, of y0 equals this. It's this, and as I've emphasized, it's the same formula. If capital Phi had a formula, the formula for the flow map, phi t, is the same formula. But all it is a change in perspective. When I think about solutions, this thing, I'm thinking of y0 is fixed and epsilon is fixed in this case, and t is the variable. This describes a vector-valued function of t, a parametric curve that if you graph it as t varies, it's a curve. It's a solution curve in the phase plane, like I was drawing 5-10 minutes ago. Whereas when I think about the flow map, I think of t as fixed and I think of y0 as the variable. The initial conditions are the variables. Or is the variable. But it's got the same formula. But it's a different kind of function. This takes real number inputs and gives you point outputs or vector outputs. This takes point inputs or vector inputs and gives you also point inputs, point outputs or vector outputs. Think of them as points. It's probably better to think of them as points. You know, we have this association between points and their position vectors, so you can think of it either way. But it's probably best to think of them as points here. Capital Phi is a function from R or some interval of R to R2, capital Phi sub y0. Cursive Phi t is a mapping from R2 to itself, but it's a nonlinear mapping, not a linear transformation. The flow itself is just the family of these functions as t varies. T can only be greater than or equal to 0 here because I can only be certain you're going to be defined for all t greater than or equal to 0, not t negative. It will be defined for some small negative t's, but not necessarily as t goes to minus infinity, because you could have vertical asymptotes, so to speak, in backwards time. If it's an attractor in forwards time, it's really a repeller in backwards time. And it can be shown, because the system is autonomous, that the flow property or group property holds, like we talked about in lecture 18a, although it's got to be for non-negative times. But this equation is true when s and t are greater than or equal to 0. Which actually means, I'm not going to say why, but we probably shouldn't call it the group property in that situation. But don't worry about it. I'll talk more about that later, in a later lecture. So that's the flow map property. And we saw in lecture 18a that this flow map property implies, and this was the punchline here, that the solution of the difference equation, where you iterate the time 1 map for a given initial point y0, will equal the solution of the differential equation. This is a difference equation up here. Yn is going to equal the solution of the differential equation IDP at time t equals n. Boldface y sub n that comes from this difference equation equals, now we go back to the capital Phi solution function of the differential equation, plug in t equals n. Okay, I illustrated this with examples in the last couple lectures. It's definitely easiest with linear examples, right? I illustrated it with examples. Now we're thinking more abstractly. The principles still work. It does need to be an autonomous equation, though. We saw in lecture 18a, in fact, with some non-autonomous examples, even though in a sense I could still define phi t in this way, the flow property, the group property didn't work. Okay. non-autonomous equations. So this is something special for autonomous equations. And it's going to be relevant in the next lecture, thinking about existence and uniqueness. But we seem to have a problem here. We don't have simple formulas for solutions. No formulas at all, in fact. Unless you, again, name the function after yourself and said, hey, everybody, this is my function, but people probably wouldn't take you seriously because, you know, they'd say, hey, you can't name it after yourself. It's already named after Van Der Pol. How can we approximate? Well, we're only going to focus on Euler's method. Euler's method can be used, though it is relatively crude compared to higher order and better numerical methods. Why? Euler's method, though it is simple, takes a lot of steps to get to the same level of accuracy as better numerical methods. Okay? So we'll use it. It's pretty intuitive, fairly simple, but it doesn't necessarily give you the best results for your money, so to speak. What is the algorithm? It's basically the same algorithm as the scalar case, except y is a vector instead of a scalar. Or y is a higher dimensional point instead of a one-dimensional point. In this algorithm, I am going to include the possibility of the right-hand side function depending on t as well, so this will apply to non-autonomous systems as well. We're going to see when we look at existence and uniqueness in lecture 20a that there's a stark difference between what happens for autonomous systems and non-autonomous systems. But the Euler's method works in either case. Pick a time interval from t0 to b over which to approximate the solution of an IVP, this one. Notice on the right-hand side that my vector field depends on t as well as y. Could be non-autonomous. Okay? Intuitively, when you're thinking about vector fields that are non-autonomous, what you really want to do is you want to imagine that as time goes by, the arrows actually change both in their direction and their length, the arrows in the vector field. And so what that means is if two solutions, and this can happen, come to the same point at different times, their velocity vectors for the curves could be different. And that can happen with non-autonomous systems. And it makes it more interesting, but it also makes it more difficult to deal with. Oftentimes, T0 is called A. In fact, when I talked about the one-dimensional Euler's method, I think I used an A there. Integral from A to B, or T0 to B. Second step, compute a step size, delta t, to be b minus T0 over n. Maybe you skip step one in terms of thinking about an interval and you just decide I'm going to let delta t be something. That's essentially what I do when I use Mathematica for this, oftentimes. Once you've got the step size, which is often some small number like 0.1 or 0.01 or 0.001, then define the mesh points, ti to be T0 plus I times delta t. So T0 is here, say. This would be T1, that would be T0 plus delta t. Then T2 would be T0 plus 2 times delta t. The width of each of these intervals is delta t here. T3 would be T0 plus 3 times delta t, etc. Tn will be T0 plus n times delta t. And when you multiply delta t by n, the n's cancel, and what that means is Tn does equal b. And Tn equals b. It's similar to numerical integration, but we're not doing numerical integration, at least not in the usual sense of the word. We are approximating a solution of a differential equation, which is a more general kind of integration. But we're not literally thinking about an integral. Next, you iterate the difference equation. This is the key step right there. That's the key formula. The new value of y is the old value of y plus delta t times the vector field at the old value of t and the old value of y. And this is pretty intuitive as well. Think about it carefully. If yi minus 1 is that point right there, And if at the given time, ti minus 1, the vector field looks like this, if this vector is f of ti minus 1, yi minus 1, could be a long vector, delta t could be small, but to find yi, you essentially move along that vector, a scalar multiple of the vector. Delta t is the scalar. So maybe this vector right there is delta t times f ti minus 1, yi minus 1. And that would mean this point right there is yi plus 1, or yi, excuse me. Okay? Using the geometric meaning of scalar multiplication by a vector and also vector addition. If the origin were right here, say, yi minus 1 as a vector would look like that. This arrow here is that thing right there, and the sum of those two things is this arrow right here, which corresponds to that point right there. And that should make sense because, again, f is the vector field for the system, and it's a velocity vector for the solution curve at any time the solution curve happens to be at its tail at a certain moment in time. Okay? So it is a pretty intuitive thing if you think about that. We hope each point, yi, is a good approximation to the true solution point for that given value of time, ti, which I'm writing both with flow notation and solution notation. You could think of it either way. Is it going to be a good approximation? Well, for one thing, it depends on what you mean by good. This is very vague, right? What does good mean? And, well, there are ways of thinking about that, but we're not getting into it. Then you can connect the dots, connect y0 to y1 to y2 to y3 with some sort of interpolation method. It's fine for this class to just connect them with straight line segments. That gives you something called a polygonal curve, which is not really a curve. It's a bunch of straight line segments put together. It might look like that. And there's an orientation as time increases. So you can think of this union of these straight line segments, this polygonal curve, as approximating this true solution curve, which will be an actual curve, maybe like that. We can do this by hand with calculator help for a small number of steps, like maybe 2. Or we can use Mathematica, for example, NestList to implement this. Time. I think I do want to finish here. It's fairly easy to apply by hand when you've got a calculator help and you've got a formula for boldface f. You just plug things in. You're working at the vector level. For my students, there are examples in the book. In the book, they also split it into the vectors into thinking about the individual components each, and that's fine. But you can think of it purely in terms of vectors the whole way if you want. Let's end by looking at Mathematica here. In lecture A, look at Mathematica again. I don't expect you to fully understand this code. In fact, it ultimately is not completely ideal. But I want you to understand the basics of it, my students. What I'm trying to do is use NestList. And as I did in the one-dimensional case, I need to create a function that's going to be a higher dimensional function to iterate in NestList. That's going to update the value of t by delta t when I iterate it. Update the value of x and y individually as scalar quantities. Little f and little g are the components of the vector field boldface f. Doing this with the Van Der Pol equation, so there's an epsilon there. I'm going to pick epsilon to be 1 and delta t to be 0.1. This is really a 3-dimensional input and 3-dimensional output. So I keep updating t, x, and y as I go, and I apply NestList, in this case 10 times, because of the last 10 here. Notice my initial condition. The first component is t equals 0, the second component is x equals 0.1, and the third component is y equals 0, giving me a list of 3-dimensional points. But I want to plot this in the phase plane, so I don't want the t's in there. This code, using something called drop, will get rid of the t's. And I'll just have a bunch of 2-dimensional points that correspond to the 3-dimensional points. I just got rid of the t's there. You can double compare these things. And then I can plot those things with the phase plane using something called list plot. Based on the initial condition, oops, let's see. Data. Okay, I actually want to go more than 10. Let's go 100 steps here. Semicolon will suppress the output. So we don't have to see it, but now we can graph it. There we go. Isn't that pretty? So solution starting at x is 0.1 and y is 0. The points are kind of melting together here because they're so close together, but they start to separate over here and here because the velocity vectors of the solution curves are further apart. There is a way to join the dots as well, but I think I'll leave it at that. And this code, I'm not going to explain it, was what I was experimenting with, and it's not fully successful. But what I was wanting to do here was to try to animate the actual flow. By essentially taking a random set of points in a small region and thinking of that as a solid set, so to speak. It's not, it's a bunch of just individual points, discrete. But if I play this, the points do start to move apart, but they stay somewhat together. You can pretend, essentially, that these individual sets are what were the images of the flow map for different values of t. And so we're seeing how the sets behave under different flow maps. Not necessarily just t equals 1 here, but a bunch of different values of t. Each step is an image for a different value of t of the original set under the flow map. And I hope you think that's kind of interesting. I think it's really cool. Thanks for watching. After ending lecture 19A with my usual goodbye, thanks for watching, I realized I forgot to show you something kind of cool. You can try to approximate that periodic solution using Euler's method if you just do more steps, like say 500 instead of 100. Then we see, based on this picture, it looks like the periodic solution is traced about like this. Okay? That other solution that we used that we were approximating with Euler's method approaches the periodic solution as t goes to infinity, and it gets to a point where you can't tell the difference between them. Now, I'll end it again. Thanks for watching.